Let's look at the next problem number 88 from this chapter number 27. So I think this is one of the tricky questions of this chapter, and so we can see the problem which is given in the figure. So you have to find out various values for this configuration. So a parallel plate capacitor has square plates of side 2.5 centimeter. You can see that on the figure, and the plate separation is 2.50 mm. So you have to change these units into SI units. So that is, you have to change cm into meter and millimeter mm into meter. So further, the capacitor is charged by the battery to a charge Q equals to 4 microcoulomb, after which the battery is disconnected. Okay, and further, a porcelain dielectric of dielectric constant 6.5 is then inserted at distance y equals to 1.00 centimeter into the capacitor. So you have to find out the effective capacitance of this capacitor for the part 1. So here the side length is 2.50 centimeter, which is this much. So you can further convert this plate separation 2.50 millimeter. It will be 2.5 times 10 to the power minus 3 meter. So the dielectric constant is given, and the distance at which the dielectric is inserted is also given. So this is 1 times 10 to the power minus 2 meters. So for the part 1, the capacitance for the portion of device that contains dielectric, you can see that some portion of the plate, that is the distance where the porcelain dielectric is inserted. So you will be able to differentiate the portion of device that contains dielectric with the portion of device that doesn't contain dielectric. So for the first part, suppose let's say the capacitance for the portion of the device that contains dielectric would be this. I think you all are kind of familiar with the formula Ke and area over D. So the area of the device that contains dielectric would be, this is the length of plate, and this is the small distance y to which the dielectric is inserted. So S times y would give us the area of that region where the dielectric is inserted, and you can just plug in all the values that we already converted into corresponding SI units. So you will be able to find out the capacitance of the portion of device that contains dielectric, which is 5.75 picofarad. And similarly, we can find the capacitance for the portion that doesn't contain dielectric. So you can obviously think about that. So this is the distance, and for the rest of the distance, this will be S minus Y. Okay, so it will be, again, this is area, and you can just plug in all the values which are kind of we are already familiar with. So this will be C2, let's say C2, and we can find C2 as 1.33 picofarad. So the total capacitance, that is C effective, would be the sum of these capacitance that contains dielectric plus the capacitance for the portion of the device that doesn't contain dielectric. So the sum would be this much. So this completes the solution for part A. For part B, so we have to find out the energy stored. So the energy stored is kind of easy, so which is the same formula that we already encounter with, that is 1 over 2 q square over c, but here c is c1 plus c2. You can further simplify corresponding values and you will be able to get this, and you can further solve this into the simpler form, and it will be u equals to q square d to epsilon naught s, and this whole expression you just have to plug in the corresponding values and you will be able to find out this. For part C, so you have to find out the magnitude and direction of the force exerted on the dielectric by the plates of the capacitor. So for part C, magnitude and direction of force exerted on dielectric by the plates of capacitor, which is kind of negative derivative of this energy stored, which is kind of negative potential gradient. So this is F equals to the derivative of this expression with respect to y. So you can take a simple derivative of that, which is this. Okay, so when you plug in all the values, that is value of q, d, k, epsilon naught, s and y, you will be able to find out the magnitude of force.